Swayam Prabha. Digital India. Educated India.
Welcome to the Organic Chemistry Paper 2. In the fourth module, we are studying about alkyl halide reactions. In the lecture 3, we will be studying about E1CB mechanism and few worked out examples. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. In this session, the topics that we will be covering include Brett's rule, E1CB mechanism, Grignard reaction, worked out examples related to E1 and E2 mechanism, and a few clues like how to solve some of these reaction mechanism problems. Let us look about Brett's rule. In this rule, what we study is basically the bridge-head carbons cannot be part of a multiple bond, that is pi bonds and double bonds cannot be formed, at least for smaller rings. So this is what is the Brett's rule. Let us look at the example here. In the corresponding chloro derivative as shown here, this loses HCl to give a alkene or the olefin, but unfortunately this reaction does not proceed simply because the bridgehead cannot form the double bond. So the reason is the bridgehead why it cannot form the double bond is basically it is going to be highly twisted non-planar constrained bridgehead. So the double bond cannot be formed at the bridgehead because there is a severely twisted non-planar constrained arrangement at the bridgehead, so it cannot form. And there are few exceptions in the large 13 or 14 membered ring bridgeheads. There are possibility of forming double bond, but in the smaller rings it cannot form. Let us look at another reaction mechanism, which is the E1CB mechanism. This is an alternative to E2 mechanism. In E2, it's a concerted mechanism or a single step mechanism, where in E1CB, it is a two-step carbanion mechanism. We have mentioned this earlier also. So in the first step, what happens is like the base abstracts a proton from the alkyl halide. It is a very fast step. This leads to the formation of an anion, which is the conjugate base. And in the second step, the base in the second step, the anion gives the electrons between the two carbons, and the leaving group is lost to give the alkene. And in this particular case, the slow step is a rate determining step, that is the step 2 is a rate determining step. Although it is unimolecular, the overall reaction is second order. Let us see how we can say the overall reaction is a second order kinetics. Let us look at some of the evidences for E1CB mechanism. The first one is the isotope effect, which we have seen earlier also. What is the primary kinetic isotope effect? In that case, if the replacement of hydrogen by deuterium, that is a lower isotope by a higher isotope, and if the rate of the reaction is affected by the replacement, then we say there is a primary isotope effect. So in this particular case, we are treating the bromide with the ethoxide ion. It abstracts the proton, and when it abstracts the proton, basically an anion is formed, and treatment of this anion with the deuterated ethanol leads to the deuterium substitution, and the alkene formed is having the deuterium incorporated as shown here. So this clearly tells that there is a isotope effect for this particular reaction. Then let us look at the rate of this particular step. The rate is proportional to the concentration of the alkyl halide, that is basically in this particular case the rate is directly proportional to the anion that is formed. And when we talk about the overall rate, we have written this like concentration of BH and the concentration of the anion divided by concentration of the starting material into concentration of the base. Since the base is used in large excess, that is a solvent, if if the alkoxide is the base, then alcohol is a solvent. So we can assume that the concentration of BH is constant. Then we can remove the term. Then we can rearrange the equation according to that one shown here. So here in this particular case, we have the rate involves concentration of two materials, two species. One is the starting material and the second one is the base. So that's why this reaction is basically called as a second order reaction. But unfortunately it is very difficult to differentiate between E1CB and the E2 mechanism. So that is the reason most of the cases these two are like completely difficult to differentiate whether the reaction proceeds by E2 mechanism, which is a single step concerted mechanism, or it is a E1CB mechanism, which is a second order kinetics mechanism. Let us look at some of the factors that affect or that favor the E1CB mechanism. One is strong stabilization of the conjugate base is very essential for this reaction. Let us take an example of a keto halide is shown here. The keto halide, basically the base subtracts a proton from the beta carbon atom, and then that produces a anion. The anion is because of the presence of the strong electron withdrawing group, the carbonyl group, the electron is pulled towards itself and the anion is shifted between the carbonyl carbon and the anionic carbon. So this leads to a intermediate, which is a resonance layer stabilized conjugate base, and if this intermediate undergoes loss of the leaving group, that leads to a elimination product where we get a alpha beta unsaturated system. And there are various poor leaving groups that can also affect the reaction. Example, the substrate with acidic hydrogens and poor leaving groups affect the E1CB mechanism. That means strong electron withdrawing groups are very poor leaving groups. For example, nitro group, keto groups, esters and cyanides are very poor leaving groups because many of these affect the E1CB mechanism. The presence of strong electron withdrawing group actually favors the E1CB mechanism. As shown here, we have a hydroxide derivative which undergoes elimination in the presence of KOH. It can lead to two type of product. One is a conjugated alkene, another one is a non-conjugated alkene. And in this particular case, the conjugated alkene is formed in large excess and the non-conjugated alkene is not at all formed in this particular reaction. And the next one is addition of Grignard reagents. Rx reacts with magnesium in the presence of ether to give RMgX, and this adds with the carbonyl compound to give the magnesium complex, and when hydrolyzing this magnesium complex leads to the formation of alcohols. And let us work out some problems. First we will see this particular example that with a suitable example how we can show E2 elimination is stereoselective. So what is stereoselective? When we say stereoselective, it is basically one of the isomer, one enantiomer basically gives one set of specific stereoisomers. So this is what is called stereoselective elimination. Let us take an example as shown here. So in this particular case, this is a mesoisomer. The mesoisomer undergoes elimination to give the cis product. So in the case of mesoisomer, here the bromine are on the same side, hydrogen is on the same side. This is simply called the Fischer projection, and it is very similar to Fischer projection, and this is converted into a Sahar's notation. So when we do that, what we do is we can keep the back carbon as it is, and we can actually move the one of the other carbon as we have mentioned here. So if the phenyl is at the top, and if we look clockwise, phenyl, bromine and hydrogen. So here it is phenyl, bromine and hydrogen is in the anti-clockwise direction. But if you look at the front carbon, it is phenyl, hydrogen, bromine in the clockwise direction. So here it is phenyl, hydrogen and bromine in the clockwise direction. So between one of the carbons, you have to retain the arrangement in the Fisher as it is, and in the second carbon we just inverse it. So that is how we can convert the Fisher notation into Sahar's notation. So as we do like this, the base can abstract a proton. So the base abstracts this particular proton, and this is lost as a H plus ion. So this bonded electrons are shifted here between this carbon and this carbon. Now the leaving group leaves to give the cis isomer as the product. So the meso starting material gives the cis isomer. And when we take the DL isomer, this gives basically the other product, which is the trans product. Let us see how the reaction actually proceeds. So here we see, if we look at this carbon, this is phenyl, bromine and hydrogen in the clockwise. Phenyl, bromine, hydrogen in the clockwise. So we retain the first carbon's orientation the same way. And in the second carbon, it is phenyl, bromine and hydrogen in the clockwise. Here it should be the reverse. So phenyl, bromine, hydrogen will be in the anti-clockwise direction. So that way we can convert the Fisher notation into Sahar's notation. So here the base now abstracts this proton. This bonded pair is shifted between these two carbons and the leaving group leaves. So in that particular case, we are ending up with a trans isomer. So this is what is called stereoselective, in a way that the meso isomer gives only the cis product, whereas the DL isomer gives the trans product. So this kind of formation is called stereoselective elimination. So that's how we can say E2 elimination is a stereoselective elimination. Let us look at the next problem. So among the following compounds, which one undergoes E2 elimination faster, and what is the reason for that? We need to identify now. We have 1, 2 and 3 cyclohexyl derivatives. So this cyclohexyl derivatives undergoes elimination reaction. We have 2-methyl and a halogen. Here again 2-methyl halogen, 2-methyl halogen. Only their orientations are different. Here all are cis isomers. Here these two are methyl and the chloro are cis, and this chlorine and this methyl are trans. Here methyl and chlorine is trans, chlorine and methyl is again trans. So we have three different isomers, and we need to find out how what are the products obtained and which one will give the product very effectively. So to solve the problem, what is the hint we have to look at is basically the draw the chair conformation and look for anti-periplanarity for E2 elimination. So one of the characteristics of E2 elimination is the anti-periplanarity. So this is a normal cyclohexyl structure we have written here. From this it is very difficult to identify anti-periplanarity. So we have to convert this cyclohexyl derivative into the chair conformation, and once we draw the chair conformation, then it becomes much easier for us to identify which one will undergo E2 elimination, because anti-periplanarity can be found in few of the substrates. We have to identify which one will undergo the elimination much faster. So some of the chloro, methyl, methyl is drawn here. All the three are cis, and in this particular case we have so this chlorine and methyl is cis, and this chlorine and this methyl is trans. So in this particular case these two are trans, these two are cis. So the same way here, these two chlorine and methyl are cis, and chlorine and this methyl are trans. Here this chlorine, this methyl and methyl, all the things are cis. That means they are all pointing upwards. And here it is pointing upwards, here it is pointing downwards. So that's how we can say whether it is cis or trans. And in the next one we have the methyl and the chlorine. These two are trans to each other. So here is a methyl and here is a chlorine. These two are projecting opposite sides. So these two are trans, and this chlorine and this chlorine both are again trans. So that means this chlorine and this methyl group are both trans to each other. So that way we have actually drawn the cyclohexyl conformation. Now we have to look for antiperiplonarity to identify which one will undergo the elimination faster. So here we have, let me draw the things completely, then we will start our explanation. So here this methyl group and this proton both are in the anti-periplanar arrangement, that is they are anti to each other and they are in the same plane. So these two are anti-periplanar to each other, and this chlorine and this proton also trans are anti to each other, and these two are also anti-periplanar. So this compound has two anti-periplanar hydrogens and chlorines are present. And this second case we have one chlorine, but the second one here is actually occupied by the methyl group, but the hydrogen is only in the axial orientation. So that means these two are not in anti-periplanar arrangement. This chlorine and this proton only are in the anti-periplanar arrangement. And in the last case, both methyl occupy the anti or the trans orientation to the chlorine. So that means this particular substrate does not have any anti-periplanar chlorine and hydrogen arrangement. So that means we can confirm which one will undergo the elimination much faster. So this isomer undergoes elimination much faster because there are two orientations, two protons are there for anti-elimination. This one will go at a moderate rate because at least one hydrogen and is present in the anti-periplanar to the leaving group. Whereas in this particular case, we don't have any proton which is anti-periplanar to the leaving group. So that means this does not undergo elimination. So that's how we can actually confirm that which product will be formed in the E2 elimination. Let us look at the next example. Here we are looking at to explain the product formation with a suitable mechanism. Olefinic alcohol is treated with HCl to give the chloro and the cyclopropyl derivative, and the other one is, this is a primary alcohol, this is a secondary alcohol, there is a methyl group here, and the rest of the molecule is same. When the first one is treated with the HCl, we get a cyclopropyl derivative, whereas when we have a methyl group here, it is subjected to the same reaction. We do not get a cyclopropyl derivative, but the same substitution product is obtained. So how do we explain this product formation? A hint for solving this problem is based on the neighboring group participation. So let us look at the mechanism for this particular reaction. So in the first step, HCl means this is dissociating as H plus and Cl minus ion, so that there is protons are present in this medium. So the lone pair of oxygen bonds with the proton to form the hydroxonium ion. That O oxygen is having the plus charge, and because OH as such is not a good leaving group, so it cannot be lost very easily, but converting that into H2O plus makes it a very good leaving group. So that is what actually happens. So this leads to the formation of a carbocation. So in this particular case, we form a carbocation after the loss of this water molecule. So the nucleophile Cl minus can attack this carbocation. So if it directly attacks this carbocation, then we end up with the normal product as shown here. But there is one more thing what can happen in this particular case is, this double bond can stabilize this carbocation because this carbon is a sp2 hybridized carbon. These two are also sp2 hybridized carbon. So all are having the sp2 hybridization. So the p orbitals will lie in the same plane. So the pi bonding electrons so the So the pi bonding electrons can stabilize the carbocation to form this cyclopropyl carbocation. Once this carbocation is formed, this carbocation can be attacked by the chloride nucleophile that leads to the observed product. So the Cl minus addition adds to the carbocation produces the cyclopropyl derivative. So this way we know the neighboring group, the pi double bond participated in the particular reaction. So this is an example of neighboring group participation in stabilizing the carbocation. When we look at the other case with the methyl group here, up to the first step formation of carbocation is very similar, but unfortunately this carbocation cannot be now undergoing the pi bond stabilization through here because of the presence of the methyl group, which puts lots of strain. So this particular pi bond cannot now form or stabilize this particular carbocation. So this undergoes the normal addition, like the chlorine adds to the carbocation to give the normal product, which is observed here. So basically, if the pi bond donates the electron to the carbocation, that leads to the strained system in this particular case. So that's the reason only one product is formed and not the cyclopropyl derivative is formed in the second case. Let us look at one more problem. In this case, we have to identify the product from the following elimination reaction. This again undergoes E2 elimination, and we also need to show the stereochemical outcome of this particular reaction. So this is very similar to the one which we had seen very recently. So instead of the phenyl group, in that case we have here a methyl group. So when this undergoes elimination in the presence of ethoxide base, what is the product we will be getting, whether we will be getting cis or trans isomer. So that is what is given here. So in the first case what we have is, so in this particular case what we get is actually, even though by looking at methyl group or both are opposite to each other, we cannot call this as a trans isomer simply because we have to follow the CAP rule. According to the CAP rule, this gets the highest priority followed by the methyl group. This is bromine is high priority, methyl is lower priority. In this particular case, methyl, that carbon is having high priority, hydrogen is having a second priority. So between these two cases, the high priority groups are on the same side. So this is the cis isomer, very similar to the cis isomer, and the actual notation is Z isomer. And in this particular case, the highest priority group bromine is here and methyl is here. So this is 1, this is 2. And in this case, the lowest priority hydrogen is here and the methyl is here. So these two highest priority groups are opposite to each other. So this is the E isomer. So that way we can say this is the Z isomer and this is the E isomer according to CAP rule. So this is the stereochemical outcome of this particular elimination reaction. Let us work out another problem. In this case, we are going to identify the product from the following reactions. There is a secondary alkyl bromide. This is treated with sodium methoxide in methanol. Then another cyclohexyl derivative is there. This is treated with the tertiary butoxide. That is potassium tertiary butoxide is used as the base in tertiary butanol. And we also have a dibromo dimethyl substituted cyclohexyl derivative. This is treated with the sodium methoxide. So we need to identify what is the product formed. Here we are using a strong base in all the cases, so we can assume that this reaction is going to lead to elimination. So let us take the first case and find out what are all the product formed. So the first product is a alkene, and the second one is a cis trans isomer, and the third one is a methoxy derivative. So these two are formed by elimination reaction. This is formed by the nucleophilic substitution reaction. So let us look how the reaction actually proceeds. So in this particular case, we have the product 1. The product 1 is formed by the abstraction of the base. The strong base abstracts a proton from this particular carbon, that is from the methyl side. This is the ethyl side. So in the methyl side, the proton is abstracted. So here the methyl proton is abstracted. So this leads to the elimination from this side, from the methyl side. That leads to the product 1 as shown here. Okay. And if the same methoxide abstracts a proton from the ethyl side, so that is from this side of that molecule, if it abstracts a proton, that is this beta hydrogen is abstracted by the base, then we end up with the cis and trans product is possible in this particular case. So these two are the examples of elimination reaction, and this methoxide base can also undergo SN2 type reaction in this particular case. So this abstracts this particular carbon and the leaving group is lost simultaneously. That leads to the substitution product. So that is the product as shown here. The third one is the substitution product. So once again we have to remember that this is a secondary alkyl halide. So the secondary alkyl halide undergoes in this particular case substitution using SN2, and elimination also it undergoes by E2. So both are competing reactions, and these two are formed. The products are formed in varied amount. The yields of the individual products vary for this particular reaction. So when we use a strong base and a strong nucleophile, because methoxide is a strong base as well as a strong nucleophile, so it facilitates both elimination and substitution reaction. And if we look at the next product, we have a tertiary butoxide, which is a very bulky base. We have two protons, one beta hydrogens are there here. This is on the terminal carbon, and this is the one which is the internal one, and let us see which one will undergo elimination. So here again the tertiary butoxide is a very strong base, but it is a weak nucleophile. So when it is a weak nucleophile, this will not undergo nucleophilic substitution reaction, so we can only expect a elimination reaction. And this being a bulky base, this particular proton is easy to abstract because this is a terminal proton, so it is easy to abstract, whereas the internal one is very difficult to abstract. So that means the product formed is the external alkene. So this is what is the product that will be formed in this particular reaction. And when we talk about the third example, so here we have actually sodium methoxide is used, which is both the strong nucleophile and as well as a strong base. So this can undergo per se both the substitution and elimination, and let us see which one happens. Since the stereochemistry of the isomers are not given here, we will be taking only few examples or a couple of examples only. We will not work out the problem for the other isomers, because in many of the cases this methyl group and this bromine, if they are in the anti or the trans orientation, then elimination will not happen in those substrates. So elimination is possible only when this bromine and the methyl group are in the cis orientation. When these two are in the cis orientation, there is a proton here which is going to be trans oriented with the respect to the bromine. So that bromine and this hydrogen can only undergo elimination. So we can draw the cyclohexyl chair conformation for this particular case. So I have put, for convenient, both the bromines are in the axial orientation, and in this particular case the methyl group is in the equatorial orientation. Here also I have put the methyl group as the equatorial orientation so that the anti-periplanarity for the elimination is possible. So this bromine and this hydrogen can be lost. The same way this bromine and this hydrogen can also be lost. So we have, let us look at how many possibilities are there. And the same way we have this bromine and this hydrogen, both are in the anti-periplanar condition. So these two can be abstracted. So this proton and this bromine, and this bromine and this proton. So we have totally one set, or this set, like two sets of protons, one of them can be eliminated, and in the other case we have one set, and in the second set we again have two sets. So but put together we have only three types of elimination possible, and we don't know which one will actually happen. So let us see what is the thing actually happening. So we have three protons anti to the bromine, and since we have only two bromine, only two of the proton can be eliminated. So the products possible are given here after elimination. We have product 1, we have product 2. Between these two products, in this product there is no conjugation. So there is no conjugation between these two double bonds. So this product is not formed, whereas here we have the conjugation. So this is the product that is formed in this particular elimination reaction. So even though there are various possibilities, at least in this particular case we have two isomers possible, but only one is formed simply because there is a extension of conjugation, or there is a conjugation exists in this particular product, whereas in the other product there is no conjugation, so this is not formed. Let us recap the summary. We have studied so far about the Brett's rule, how the bridgehead cannot, in a smaller ring systems, how the bridgehead cannot form a double bond, that we have seen, and in the E1 CB mechanism what is the difficulty in comparing it with the E2 mechanism, and how to determine the rate. All those things we have studied about the E1 CB mechanism. We also studied about Grignard reactions, the basic mechanism of Grignard reaction, and we had studied a couple of examples how to solve the elimination problems, and we also have studied some of the clues regarding how to solve the reaction mechanism. With this we conclude this session. Thank you.